Hello and welcome to this training session on setting up and running a Darrieus vertical axis wind turbine, VAWT, CFD simulation using ANSYS Fluent. A vertical axis wind turbine has its main rotor shaft positioned perpendicular to the ground and transverse to the wind direction. This configuration allows it to capture wind from any azimuth angle, making it particularly advantageous in locations with turbulent or shifting wind directions. There are three main types of VAWTs: the Savonius, which operates on drag forces, the Darrieus, which uses lift generation, and the H-type, a modified Darrieus design with straight blades. In this project, we simulate a Darrieus-type VAWT to validate the results presented in a published study titled, The Darrieus Wind Turbine, Proposal for a New Performance Prediction Model Based on CFD. The setup is based on a 2D simulation featuring three NACA 0021 airfoil blades with a turbine diameter of 1010 mm. Though it's a 2D model, a 3D view of the experimental setup helps to better visualize the actual design. The geometry is created in ANSYS Design Modeler, and the mesh is generated using ANSYS meshing. Since the problem is highly sensitive to grid quality, care was taken to avoid coarse boundary layers or sudden changes in element size, which could lead to convergence issues or inaccurate results. As seen in the mesh visualization, we have well-structured elements in the rotating domain, stationary domain, and especially around the blade surfaces. A total of 904,018 quad and triangular cells were used to ensure sufficient resolution. We start the simulation in Fluent by importing the mesh using file >read mesh, and then verify boundary zones using the display feature. The setup includes one inlet, one outlet, a rotating inner zone, and a stationary outer zone. Connected via non-conformal interfaces. Since the turbine blades rotate continuously and the flow field changes over time, we select a transient solver. This is essential to capture the unsteady aerodynamic behavior, including blade vortex interaction and periodic lift forces. Pressure-based solver is used, as it is suitable for incompressible flow regimes typically seen in wind energy simulations, where flow speed is much lower than the speed of sound. We choose the K-SST turbulence model, which is a hybrid model combining the accuracy of the K-omega formulation near walls with the robustness of K-epsilon in the free stream. This model handles separation and strong adverse pressure gradients better than traditional two-equation models, which is critical in rotating blade simulations. For boundary conditions, the inlet is set as a velocity inlet with a speed of 9 ms. Turbulence intensity of 1%, and viscosity ratio of 10 to model moderately turbulent conditions. The outlet is a pressure outlet with zero gauge pressure, with the same turbulence settings as the inlet. Blade walls are treated as stationary no-slip walls, reflecting realistic blade fluid interaction. The simple algorithm is selected for pressure-velocity coupling. Simple stands for semi-implicit method for pressure-linked equations. It iteratively corrects pressure and velocity fields to enforce mass conservation in incompressible flow. All spatial discretization schemes are set to second order for improved accuracy. The transient formulation is set to first order implicit, which is more stable and suited for simulations where solution changes are gradual over time. As wind turbines require time to reach a dynamic steady state, we monitor a key variable such as the moment coefficient, cm, of the blades. Typically, after 5 to 6 full revolutions, the values stabilize. To monitor this, create a report definition for moment, select the blade surfaces, and specify the z-axis as the axis of rotation. This is essential because rotation occurs about the vertical z-axis in 2D setups. To correctly calculate the moment and related performance metrics, go to reference values and input the correct area and velocity, as these parameters affect the dimensionless coefficients. We use hybrid initialization, which combines potential flow and standard initialization techniques to offer more realistic, starting values for velocity, pressure, and turbulence, especially useful in rotating flow setups. To generate an animation, go to Contours, select Velocity Magnitude. For time step settings, set the time step size to 0.000499358 seconds with 82 time steps and 50 iterations per time step. These values are selected based on blade rotational speed and mesh resolution to ensure accuracy and convergence within each step. Finally, Fluent's post-processing tools allow us to visualize velocity fields, pressure distributions, and turbulence intensity contours. These help us analyze flow behavior, blade loading, and wake structure. Additional contours like Y+, vorticity, and turbulent kinetic energy can be created as needed. This concludes our training on simulating the Darrieus VAWT using ANSYS Fluent. The simulation shows good agreement with the validated study. And offers a powerful approach to understanding and optimizing vertical axis wind turbine performance.
When the simulation is finished, we can see that a monitor has been created to calculate the coefficient of moment, or CM. At the beginning, up to about 600 time steps, the monitor shows some alternating or fluctuating behavior. After that, the pattern becomes stable and very similar throughout the rest of the simulation. Our main goal here is to validate the results from the reference paper and compare them with the figures shown there. In this training video, I will explain how to calculate the tip speed ratio, also known as TSR, and how to calculate the power coefficient, or CP. When we compare this result with the article, we can see that for a tip speed ratio of 2, the average CP value is very similar to our simulation result. This confirms that our model and calculations are consistent with the data presented in the paper.
To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.